know if you can hear.
We can hear you, sir.
Good, good. And you can see the screen, right? Geological structures.
No, sir.
Because
Just a
Stop stream.
it's your face that showing.
Oh, just my face. Okay. Okay. So I'll stop sharing. Can you now see the screen?
Yes, sir.
Yes, sir.
Okay. All right, just a quick one. Have you guys started looking at the maps? Have you started looking at maps by Professor?
Yes, sir.
Okay, so you started looking at the structures on maps, right? Have you? So what structures have you looked at so far? See, you're breaking up. You're breaking up. You're looking at what? All right, map skills. Okay, so you've not started looking at structures. Okay. All right. I said today I'm going to give you guys like a quiz, right? Did I tell you that? I can. You guys are not quiet. What is happening?
Yes, sir.
Okay.
yes, sir.
All right. All these guys that are coming in after the start of the class, they don't know that I don't have that time to be admitting them in. I won't have time to be admitting people in when I start the lecture, and that's why I'm just taking my time. So we now have how many people do we even have here? Almost 80 people. Because I said I wanted to give you guys quiz, right? Oh my goodness. I've never had 80 people here once. 84. All right, have we settled in? Can I start? All right, let's begin. So since you can see my screen, let's begin. Who can remind me of what we did last week? Say again? Say again? No. All right. Okay, so we talked about fractures, joints, and faults, right? Okay. So today we are going to a different set of structures called folds. Different sets of structures called folds. Okay. and I believe you must have heard of that before. So let's begin. Let's begin to talk about folds um, here. All right. Okay. So the objective, the learning objective for today is to describe the different types of folds. Describe the different types of folds. Okay? And then we are also going to explain, all right, the way we classify, folds. The first thing, define and describe the different types, okay? More or less like we're talking about here. When I say describe the different types, we want to talk about the anatomy of folds. So when you see folds, how do you describe the orientation of a fold? All right, the different parts of a fold. And then we're going to talk about the classification of fold. And then we'll finish up the class talking about how we interpret, right, folds on map. Folds on map. All right. I might switch to another slide, okay, towards the end, and show you guys, how what to look out for when we um when we come to talk about folds on map. So that's very important. We'll talk about that. Okay. So all I need you guys to do is to listen up. Go to a quiet place. Don't get distracted. Listen up and make sure you are in a quiet place where you can really understand some of these concepts. Very important. All right. So, what are folds? What are folds is the main question here. Now, these are different from faults. Remember, we said force is a fracture where you've got a relative displacement between blocks. Okay, it's a fracture where you get a relative displacement between blocks. Obviously, one block would have moved relative to the other. All right, so you must have that displacement. But in the case of folds, folds are formed under compressional stress. Okay, they are formed under compressional stress. Where is my? I thought I had. Okay, good. They are formed under compressional stress. Can you guys see my cursor? Can you see my cursor?
Yes,
Yes, sir.
Good. They are formed under compressional stress, and they are a type of ductile deformation. Did we differentiate between what you call ductile and brittle deformation? Have we done that?
yes, sir.
Yes, sir.
Okay. It's in your note, right? Is it?
Yes, sir.
All right. So it's a type of ductile deformation formed under compressional stress. All right. Compressional stress. And what are they really? They are wave-like bends in layered rocks that represent strained rock in a ductile manner. So on the screen here, what you see is, a rock that is showing, or an outcrop that is showing folds. All right, just a sec. Just a sec. It's an outcrop that is showing a fold. All right. Wow, these people coming in late now are distracting me. All right. So I don't know if you guys can see the figure on the right hand side of this slide. You can easily trace, okay, I can come here and trace, a layer in this fold. Can you see what is happening? Can you guys see?
Yes, sir.
All right. So you can see that it's a wave-like bend in layered rocks. So obviously what you have here are layered rocks, all right? But you can see that these layered rocks have been compressed, all right, to form these bends, these wave-like bends. So originally, these rocks were, remember the principle of original horizontality? Do you guys
Yes, sir.
remember the principle?
Yes,
Yes.
sir.
So these rocks would have been laid in this manner, right? Laid down in this manner. And then when you apply stress, compressional stress, okay, compressional stress to these layered rocks, what you then get is, is this kind of folds. These rocks will now form this train of folded layered rocks. Do we understand this? So in your exam, if you see what is a fold, right? You just need to tell me there are wave-like bends in layered rocks, okay, that are formed by compressional stress and they represent ductile deformation. Does that make sense?
Yes, sir.
Right. So
Yes,
please
sir.
make sure that you understand the meaning of, of fold. All right. Now let's go forward. So this example is from a place called Docksett, all right, in England. Right. Specifically, it is in the Lookworth Cove, right, cove of Docksett, England. All right, folded sedimentary rocks. Now let's talk about the geometry of folds. This is very important because when you begin to map folds, you need to understand the geometry, right, of folds for you to map it correctly. All right, you need to understand the geometry of a fold for you to map the folds correctly. Now, if you look at this schematic, right, it's it's it looks similar to the previous slide where we saw a natural outcrop where we had folded layers of rocks. All right. In fact, on here, what you see is how many layers? One, two, three, and let's say four here, four layers. All right. And you've got two folds here. One, okay, one and two. Okay. In between these two folds is, the syncline, okay, on here. All right. Now, let's begin to think about the nomenclatures here for geometry. So we've got two folds. The first thing I want to let you know is this word called anticline. Okay, anticline. So an anticline, it's an upward arching fold. Upward arching fold. So when you say upward action, right, it means that it's forming, the crest is at the top. The crest of this fold is at the top. Okay, and you can see the limbs dipping away from the crest. Okay, the limbs are dipping away from. So when we say limb, it means one half of the fold, one half. And you can see that they are clearly dipping away from the crest. Okay, so it's an upward arching fold. While a syncline, on the other hand, is a downward arching fold. All right, and you can see the limbs dipping towards the center of the fold. All right, on this other one, the limbs are dipping away from the center of the fold. Now, know the difference between anticline and syncline. Very important. Now, can you see this plane over here? Can you see this plane?
Yes, sir. Yes,
All
sir.
right. You see this plane here? This plane is termed the axial plane. And the axial plane divides the fold into two limbs, limb 1 and limb 2. All right? It divides the fold into two limbs. The other thing you need to know here is that on top of the fold, all right, the trace of this axial plane is called the hinge plane, or the hinge line, I should say. All right, that's directly on top of the fold. When you trace that axial plane, it is called the hinge line. Hinge line. Are we still together? So this is for anticline. When you come to syncline, it's still the same thing. You've got the axial, you can see the hinge line here, all right? And on this second fold, what you have is the axial plane, and then again, the hinge line. There are other terminologies I'll bring to your notice as we go ahead, all right? So take note of that, hinge line and the axial plane. These two terminologies are very important, because when we begin to classify folds, okay, they will come to the fold. All right. When we begin to classify fold, you see that these two terminologies are quite important for you to understand. Okay. Now we've defined folds, right, and then we are now talking about some important terminologies as it regards the geometry of fold. Other terminologies you need to know about is that you've got the hinge area, right, which is around the crest of the fold. We said this is the hinge line. We said this is the hinge line, all right, and it's the trace of the axial plane on the fold, all right. This is the axial plane or axial surface, all right. I want you guys to follow this because you need it, okay. This is the axial plane of the fold, all right. The other thing you see is inflection point. That inflection point talks about where the fold, is a point on the limb where, there's a change of curvature, all right? And obviously you can see that there's a change of curvature here. That is the inflection point. There's a change in the sense of curvature, all right? And then we've talked about the axial plane or surface that divides the fold into two limbs, okay? And then when we talk about profile plane, you can see that the profile plane is perpendicular. The profile plane is perpendicular to the axial surface or axial plane. Profile plane is perpendicular, right, to the axial surface, okay? Please take note of that. What time is it now? So I'll stop admitting people into this meeting in 2 minutes because it's already 9 o'clock. All right. I gave you guys time, enough time. All right. So anyone that comes after 9, right, will not be admitted in. So we've talked about axial plane, profile plane, inflection point. We've talked about hinge line, all right, as well as the limb. Other things that you need to be aware of is that a fold has what we call interlimb angle, all right? And that interlimb angle, so if you take one limb, all right, and another limb, okay, this angle in between, all right, is the interlimb angle, all right? So the angle between fold limbs as measured from the profile plane, remember the profile plane is perpendicular to the axial plane, all right? It's called the interlimb angle. You'll see why this is important when we come to the classification of folds, all right? That is also important, all right? And then we finish off with those terminologies talking about amplitude, all right? The amplitude essentially is this length here, this length here, okay? And then The wavelength is this length here. Okay? And then the arc length of the fold is when you take the limb, right, and you measure from one limb to another. All right, take the arc. Okay, that gives you the arc length of the fold. All right. Who can then remind me of some of these terminologies we've talked about? Number one. Who can remind me of these terminologies? Number one.
Interlimb angle.
Anticline.
Anticline, yes.
Syncline.
Syncline, yes.
Axial plane.
Axial plane, yes.
Inflection point. Hinge line.
Inflection
Inflection
point,
point.
yes.
Limb. Profile plane.
Profile plane, yes.
Like
Interlimb.
Interlip angle, yes.
Interlimb angle. The limb.
All right. Please remember, not just mentioning the name, remember what all of this stand for. All right. Remember what they stand for. Very important. All right. Now, having defined fold, you said folds are wave-like bends in layered rocks, okay, that are formed by compression or stress, all right, and they form in a ductile manner. We've talked about the various terminologies as it has to do with the geometry of folds. Now, the next big question is, how do we classify, right? How do we classify folds? All right. We can classify folds, right, based on, in fact, not just 4 components, but I will now add a 5th one, right, based on what? Deep, isogon. And I'll come to see what that means in a bit, all right? Deep isogon. Okay? So the first way we classify fold, we look at fold shape in 3 dimensions, in 3D. Okay, fold shape in 3D. And when we talk about fold shape in 3D, you can classify folds as number 1, cylindrical fold, and number 2, non-cylindrical. Are you still together?
Yes, sir.
Right. So we can classify folds in 3D. The shape of the fold in 3D as cylindrical and non-cylindrical folds. Okay? Now, that is one way we classify folds. Who is this Chukwu Buka? Please, can you mute your mic? Who is this Chukwu Buka? Please mute your mic, please.
Maybe after I don't know why my network is working.
All right. So we have both cylindrical folds and non-cylindrical folds when we try to talk about the fold shape in 3 dimensions. And then if we think about fold facing as a criteria for classifying fold, we have upward facing folds or downward facing fold. And this is where we now have what? Anticline. Okay? Anticline. Do you still remember? Anticline and what? And what?
Syncline.
Syncline. That is when we think about whether the fold is upward facing or downward facing. We'll come to talk about this in a bit. And then there's what we call the fold orientation. The fold orientation, we'll talk about that. And then there's what we also call the fold shape in profile plane. What is the profile plane again? Do you remember?
It's perpendicular to the axial surface.
Is perpendicular to the axial surface. I like that. Yeah, so we have the axial plane, and that is a useful tool for classifying folds. And last but not the least, we have the deep isogons. Deep isogons. That's another way we classify folds. So these are the 5 criteria we want to use to classify folds. The reason why these are important is because when you now begin to interpret folds on maps, right? It's important that you understand the way the folds are classified. All right? The ways the folds are classified. Now, let's begin to think about this one after the other. All right. Remember the first classification, fold the shape in 3D? This is exactly what we mean. For a cylindrical fold, so this is 3D classification. Look at this A diagram. Can you see that the hinge line, right, is what? Straight. And because the hinge line is straight, it is called a cylindrical fold. All right? Because we can wrap the fold around what? A cylinder. We can wrap this fold around a cylinder because the hinge line is straight. All right? But you see these other two, the B diagram and the C diagram, you can see that the hinge line is bent. All right? The hinge line is bent. So you cannot wrap this A and B diagram around the cylinder. So it is called what? Non-cylindrical fold. Do you understand that distinction?
Yes, sir.
Good. So this is classification based on the fold shape in 3 dimensions. Now, if we go ahead, okay, we can classify fold in terms of the fold facing, okay, as what? Downward facing, which is an anticline, okay? There was a term we used, we said upward arcing fold, right? When we began. And then syncline, we said downward arcing fold. But again, we can change that to downward facing and upward facing fold, okay? But do you know that we only use this term anticline and syncline, okay, when the age, right, the relative ages of the folds, of the layers, of the beds are known. So here we can say this is an anticline because we know for sure that the older beds, we know the difference between the younger and the older beds. So the older beds are on the concave side. This is the concave side of the fold. Okay? And the younger beds are on the convex side of the fold. So this is the convex side. So if you have something like this is the concave side, and this is the convex side of a fold. Are we still together? So the older beds are here, okay? The older beds are on the concave side, and the younger beds are on the convex side for an anticline. But for a syncline, the opposite is the case because the younger beds, right, are now on the concave side, and the older beds are now on the convex side of the fold. Do you understand this?
No, sir.
Please
You
call
said-
me again, sir.
If we know the relative ages of the fold, like we can tell of the folded layers. So if we can tell that, do you remember the principle of superposition? The principle of superposition.
Yes, sir.
Yes. What does that principle say?
Rock layers are arranged when the older layers are um at the bottom and the younger layers are at the top.
Okay. Okay. So the older layers are, you know, so beds are always in an undisturbed sequence. All right. In an undisturbed sequence. So a bed is always younger than the one below it and older than the one above it. That is the principle of superposition. Now, when you look at this, uh, uh, so let's draw this again. Okay, let's draw this again. So one, okay, is younger, and two is what? Older. All right, one is younger. So a bed is always younger than the one below it, okay, and older than the one above it, okay. So in this case, two is older and one is younger. Now, when you subject this to compressional stress, okay, you get this kind of geometry, right? For you to have an anticline, okay, there's what we call convex and concave, right? The convex, so draw a C. The convex is the inside of the C. The concave is the outside of the C. All right. So if you invert this, right, you can see that the older beds are on what part here? The concave side, inside the C, and the younger beds are on the outside of the C, so they're on the convex side. That defines an anticline. But we can only say this because we know the relative ages, which one is older and younger, the relative ages of the layers. But on the other side, okay, if we look at this example here, you can see now that the younger beds are now on the inside of the C, and the older beds are on the outside of the C, which is the convex side. So that means that this is now a syncline. Does that now make sense to you?
Yes, sir. Thank you, sir.
Good. We can only say anticline and syncline, use these terminologies, if we know the beds that are younger and the ones that are older. That is the only time we can use anticline and syncline. But let's say we don't know the ages of the beds, we cannot use the word anticline or syncline. Instead, we're going to use what we call antiform or synform.
So please can you come again?
If we don't know the relative ages of the bed, all right, if we don't know which is older or younger, we use antiform, okay, or synform. Okay, antiform or synform. And we say this because in a complex region like this, okay, you can see how this bed has been, deformed. All right, you can see how this bed has been deformed in this manner. Can you see?
Yes, sir.
All right. So if you follow the trace of those bed, okay, ideally in a very simple region, you have an anticline, right, and a syncline. An anticline and a syncline. But you see that in this deformation, in fact, the fold has been overturned. Can you see? It has been overturned in this direction. And because it has been overturned, it is now difficult to know whether one layer is older than the other layer because it has been overturned. And because it has been overturned, it's appropriate to use the word synform. So this, right, is a synformal anticline. All right? A synformal anticline. All right? An anticline because you can see that this upper portion here should be an anticline. But because it's been overturned, it's now a synform. So it's now a synformal anticline, and this is an antiformal syncline. Don't get confused. Just stay with the explanation. Stay with this explanation. If we know the relative ages, we use anticline and syncline. If we know which bed is older or younger, if we don't know which bed is older or younger, we'd rather use synform and antiform. Let's keep it simple. All right, let's keep it simple. All right, let me not dwell too much on this. All right, good. So that is the number two way we classify food. We said we classify food in terms of the shape in 3D into what? Into what?
Cylindrical and non-cylindrical food.
Right. The second way is that we classify foods in terms of the food facing into what?
Upper.
Upward facing and downward.
Food.
Okay, so syncline and anticline is synform and antiform. Okay. And then in terms of the fold orientation, all right, we look at the interlimb angles. All right. So you can classify shapes, fold shapes in what cross section depending on the what interlimb angle. And in this regard, there are 4 classifications here. Isocliner, all right, 0 to 10 degrees for the interlimb angle. All right. And this is what it looks like. Okay. A tight fold, which is 10 to 60 degrees. This is what it looks like. Open fold, which is 60 to 120 degrees. This is what it looks like. And last but not the least, gentle fold, 120 degrees to 180 degrees. All right. 120 degrees to 180 degrees. There are other classification under this criteria, right? You have rounded fold, and that has to do with the way the fold is rounded in cross section. Angular fold, with the way it looks angular at the crest. Chevron fold is so sharp, all right? Chevron fold, and then box fold, all right, because it is rectangular in cross section. Are we still together?
Yes, sir.
Yes, sir.
All right. Now, this is one way we classify food. All right. And then the 4th way we classify food is by thinking about their orientation. Their orientation. And when we talk about their orientation, we're talking about the orientation of their hinge line and axial plane. Do you know why axial plane and hinge line are important? Because we can use them to classify the food. And this is very important because in this regard, we have 7 types of fold. The first one is horizontal normal. All right. For horizontal normal, you can see the hinge line is straight. Okay. And then the axial plane is vertical. So this is an upright standing fold. All right. Horizontal normal. Axial plane is horizontal. Hinge line, all right, is normal. Are we still on the same pedestrian? The axial plane, the hinge line, all right, is horizontal. The axial surface is vertical. It's normal. Okay, that will give you an upright fold here, right? And then look at what's going on here. Can you see that? Are you guys see that? I said, look for a quiet place. Look for a quiet place. There's someone called Temi here. You can clearly see that the guy is trying to fly back. My goodness. Can you all see this second example here? Plunging inclined, right? What is happening to the hinge line? Am I talking? Hello? Yes.
So the slide just changed now.
Change to what? What can you see now?
See the same slide, the food classification.
Yeah, so you can see the fourth classification slide, right?
Yes, sir. Like a cubic diagram.
Yeah, so you can see that we're trying to talk about food classification in terms of the orientation of the hinge line and the axial surface or axial plane, right? And I've showed you what an upright fold will look like. The hinge line is horizontal and the axial surface or axial plane is normal. But for a plunging incline, you can see that the hinge line is plunging, all right, no longer horizontal, and then the axial plane is inclined in this direction. It's not normal, all right. The opposite of this plunging normal is that you can see that the hinge line is still plunging in this direction, but the axial plane now is no longer inclined, but it is vertical. That is normal. All right. Here you can see that the hinge line is horizontal, but the axial plane has obviously changed its orientation to being inclined. So this is horizontal inclined. All right. Then all of a sudden, when the hinge line, okay, is horizontal, okay, but the axial plane is no longer vertical but horizontal, it becomes a recumbent fold. Can someone say recumbent fold?
Recumbent fold.
Recumbent fold. Yes, good. So because why is it a recumbent fold? It's a recumbent fold because the axial plane is horizontal. All right. And then, the axial plane could take all sorts of orientation, a reclined fold. All right. You can see that the axial plane is overturned, and then it could be vertical. Okay. And that becomes a vertical fold. So when we think about the orientation of the hinge line and the axial surface or axial plane, we have like 7 types of folds. All right. So this is one classification. And the remainder of the slide shows us, just a sec, shows us outcrop orientation that fits some of these types of fold we've talked about. So this is horizontal normal, all right? Axial plane is vertical, hinge line, although we can't see on the outcrop, but we assume that it is horizontal. All right. For this example, the axial plane is inclined. You can put in a drawing here for the axial plane. You can see it's inclined, and we figure that the hinge line is horizontal. All right. And then for this other one, you can see that the hinge line looks like it's plunging towards us. Can you guys see that? Hello?
Yes, sir. Yes, sir.
Yes, sir.
It's like the hinge line is plunging towards us, but the, what they call it, the axial plane looks like it is, vertical. All right? So this is plunging normal. And then for this one, it looks like the axial plane is now what? horizontal, no longer vertical. All right. So this is a recumbent fold, and then this is a vertical fold. You can stand on here. All right, and look at the axial plane of this fold. Has been vertical. All right. Good. The last classification, the last criteria for classification is what? Deep isogon. Deep isogon. When we talk about deep isogon, we mean that we're talking about lines that join points of equal deep. All right, points of equal deep. And when we talk about this classification, there are two types of folds. They can either be similar folds or parallel folds. This class A1, 1B, 1C, all right, are called parallel folds. And I'll show you why. Why this one, class 2 and class 3, are called similar folds. Okay? And the question is, why are they called parallel and similar folds? They are called parallel or similar folds because in similar folds, you have the bedding shape remains the same from bed to bed. So just like so. Can you see this shape here?
Yes, sir. Yes, sir.
Right? The shape is consistent from bed to bed. And for you to have this sort of fold, it means that you have to move material from the limbs of the fold to possibly the hinge area. All right, this hinge area. You have to move materials from here. You see how thin this limb area is? And that's because for you to maintain this kind of fold, you have to move materials from here into the hinge area. Okay? That is so this is an example of similar fold. Similar fold. All right? Similar fold. And look at this orientation here. So these lines are joining places where you have on the bed where you have equal deep. Equal deep. Can you see how this area is thin? Thin. Thin. And that is because you have to move materials from here to here, from here to here, to maintain similarities of the shape of the bed. Do you get that? Yes, all right.
Yes, sir.
I said you can classify folds in terms of deep isogon. All right. And when we're talking about deep isogon, we are talking about lines that join areas of equal deep in a folded bed. Because of that, you have two types of folds in this criteria. The first one is similar fold. Similar fold, you have the same shape of the beds as you go from bed to bed. For you to have the same shape, it means that you have to move materials from this limbs area to the hinge area, okay, to maintain the same bed shape. And because of that, this limb area is going to be thin compared to the hinge area. That is why class 2 and class 3 are called similar fold, because you can see how big the hinge areas are, right, compared to the limbs, because materials have been moved from the limbs to the hinge area. That's because we want to maintain the same shape of the bed from bed to bed. Alternatively, we can talk about parallel folds. Parallel folds, you want to maintain the same thickness from bed to bed. And this is an example of parallel fold. Parallel fold. All right? For parallel fold, it then means that you maintain the same thickness from bed to bed. Because you are maintaining the same thickness from bed to bed, what that simply means is that the shape of the fold, right, is going to change, right, from layer to layer to maintain the same thickness throughout the fold. That is why here you can see that because you want to maintain the same thickness, the shape of the bed will change from bed to bed. That is why this is parallel and this is similar to two types of food when it comes to deep isogons. Similar food, the shape is maintained from bed to bed, and then for parallel food, the thickness is maintained from bed to bed. All right. Okay. Now, where does all of this matter? We've talked about 5 criteria for the classification of foods. Okay, for the classification of foods. Now, let's say you go into a terrain where you had no clue as to, the orientation of the beds, right? And that is because, the beds have been eroded, okay? Leaving behind what you now see as, just series of, vertically stacked beds, all right? What are you going to look out for? So the big question is here that how do you tell the presence of an underlying anticline or syncline in an area that has been eroded to a plane? All right. So you can see that, let's assume this is the erosional surface. Can you all see what I'm drawing?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. This is now the erosional surface. You don't have access to the subsurface, so you don't know if this is a syncline or if this is an anticline. The only thing you know is that you go to the terrain and then you've seen, you are seeing beds that are doing this, okay, that are looking like they are now vertical, right? And you stand here as a geologist. Okay, so you're standing on top of here. Okay. I hope you guys are seeing my cartoon. All right.
Yes, sir.
Good. All you need to do as a geologist is to begin to observe this layering in the rocks and take what? Strike and what? Strike and what?
Deep.
Deep.
Right. Strike and deep of the layers. Strike and deep of the layers. So you can look at this layer. Let's assume this layer here is this layer here. All right, this first layer here. Okay. What you observe is that it's as though the beds are striking in this direction. All right, but they are dipping in this direction, right? By what? 25 degrees. Okay, 25 degrees. Are we see together?
Yes, sir.
Okay. You move to this layer, you see that the strike, okay, is kind of the same with your previous measurements, but now the beds are dipping in the opposite direction, right? By what? 10 degrees. All right. Remember, this top has been eroded, so you have no clue as to whether this is an anticline or syncline. But what are your numbers telling you? You move to the next line, right? It's striking in the same direction, but it's dipping 25 degrees opposite to the previous bed, this bed here. Okay? You cross that. You go to the next one. You go to the next one, and you see that this bed is dipping in this direction. It's striking in the same orientation, but dipping in this direction by maybe another 25 degrees. What does that tell you? It tells you that if this bed is dipping in this direction and dipping in this direction, it can then only be, so in cross section, it can only be a trough, an anticline, just as you see here. Does that make sense?
Yes, sir.
Good. And because these two are dipping away from each other, right, this can only be an anticline. The question again, how do we tell the presence of an underlying anticline or syncline in an area that has been eroded to a plane? You have no access to subsurface. All you have access to is your compass clinometer which you use to take measurements in the field: strike and dip. Now, having taken strike and dip of the beds, what you've now found out is that because these beds are striking in the same direction but dipping, right, in towards each other, it's definitely going to be a syncline. And on the other hand, because they are dipping away from each other here, okay, it's going to be what? It's going to be what?
Anticline.
An anticline. All right. So the other thing you notice is that when you date the rocks, all right, you will find out that the younger beds, okay, are exposed at the surface, okay, for how will I put it? The oldest beds, right, are exposed at the surface for an anticline. All right, remember it has been eroded. So the oldest bed will be exposed at the surface, while for a syncline, the youngest rocks will be exposed at the surface after erosion. All right, and this is key. Let's say you date the rocks. All right, the youngest rocks will be exposed at the surface after erosion, and then the oldest bed will be exposed at the surface after erosion. Please take note of that. It's quite important. So in order to wrap up, okay, in wrapping up, erase. By measuring the strike and dip of exposed sedimentary rocks in the field, right, and plotting on a geologic map, we can tell whether the underlying structure is an anticline or a syncline in an eroded area. Does that make sense? All right. Cool.
Yes, sir.
All right. I thought to bring that to your notice. The other thing I wanted to show you here, you can see what is written here, right? Fold, right? In which the hinge line is not horizontal. And I showed you that already, right? Where the hinge line is not horizontal, right? It is called a plunging fold. What criteria is used to define this? What criteria? We talked about 5 criteria. Which one of them fall into this category?
Fold classification based on their hinge line and axial surface.
Good. Fold classification based on hinge line and axial surface. Now, you can see in this diagram here that the hinge line is plunging in this direction. All right? It's plunging in this direction. You can see how they are plunging in this direction because they are not horizontal. All right? But then the axial plane is vertical. All right? So this type of fold is called plunging what? Plunging what?
Fold.
Plunging normal. Plunging normal. Because the hinge line is plunging, right? But the axial plane, you can see, is vertical, all right? So this is an example of a plunging normal flood. A plunging normal. So this is the anticlinal part of it, and this is the synclinal part of it, all right? So in a syncline, we say the youngest formation are exposed at the surface, Okay, and then in an anticline, once it's eroded, the oldest formation are exposed at the surface. It's important you know this. And then let's finish off with this. Structural domes and basin. All right. So this first one here shows us a dome. In a dome, right? Structures in these are structures in which the beds dip away from the central part. All right. Sometimes called the doubly dipping anticline. You see the orientation, right? Let me draw this for some of you to see properly. All right. You see the orientation of, you see this sign here? This sign is basically showing us that the beds are basically dipping away from the center. The beds are dipping away from the center. All right. Such that the oldest layers are exposed at the surface. All right. So this is a domal structure. All right. Or a dome. The opposite is the case for a basinal structure where the beds dip towards a central point. All right. Sometimes it's called a plunging sink line. All right. So the oldest layers are found at the middle. And here, the oldest layers are found at the middle here. And here, the youngest layers are found at the middle. All right. Something for you to think about the domes and the basins. Do we understand this? Do we understand that?
Yes, sir.
All right.
Yes, sir.
Let me quickly show you another slide, but I'm not going to give you access to this slide. Okay. I'll just quickly show you something here. All right. So this is a classification based on interlink angle. We've talked about this already, right? Isoclinal to gentle. Did we?
Yes, sir.
Good. We talked about the geometry of folds. All right. We talked about inflection points where there's a change in curvature. All right. We talked about classification that is based on layer thickness. We talked about parallel folds and similar folds. So this is an example of what? This figure here is an example of what?
And similar folds.
A similar fold, and that is because you've got what?
You have
Why is
similar
it called
thickness.
a similar thickness?
Similar shape.
Similar shape from bed to bed, and this is an example of parallel fold, similar thickness from bed to bed. All right. This is an example of a cylindrical fold. A cylindrical fold. Why is it called a cylindrical fold? Hello. Why is it called a cylindrical fold?
Because you can fold it over a cylinder.
You can roll it over a cylinder, and then the hinge line is straight. All right. Okay. I've showed you this already. Okay. We don't know the age of the bed, the relative ages of the bed. So this would typically be an antiform. All right. And this would be a sink form. You can see in map view. So this is in cross section. In map view, this is what you get. You can see that this bed is dipping in this direction, and this one is dipping in this other direction. All right. For a sink form, this bed is dipping in this direction, and this is dipping in this other direction. All right. Please, can we unmute our mics? The reason I'm showing you this slide is
Yes.
can we mute our mics, please? All right. The reason I'm showing you this slide is because I wanted you to see, like, compare what a bed will look like in 3D and then in map view. All right, in 3D and then in map view. This is an upright horizontal bed. Okay, this is an inclined horizontal bed. All right, this is an overturned horizontal bed. This is a plunging fold because the incline is plunging and the axial plane is vertical. All right, and this is what it's going to look like in map view. All right, upright plunging antiform, upright plunging syncform. All right, and you can see that the beds are dipping away from each other. So if you produce a map, when you go to the field, when you produce a map, this is what it's going to look like. All right. Doubly plunging fold, we talked about it for our last slides. Recumbent and inclined fold, we've talked about all of this already. Reclined folds. And then I usually will give this sort of exercise. Can you all see this? Hello?
Yes, sir.
All right.
Yes, sir.
Usually I will give you this sort of exercise where this is called Sheep Mountain in Wyoming, in the United States. All right. And, erosion has cut the flanking sedimentary beds into low ridges in places cut into V shapes by transecting drainage. All right. What we're saying is that this is a residual surface because it has undergone weathering and erosion, and now this is what you have for the surface. You're going to use a transparent overlay, all right, like a transparent sheet. You place it on this figure and you try to trace the outline of the major structures. And then you describe the structure of the sheep mountain in much more details using the terms introduced in class. All right. For instance, you want to talk about, the remnant structures and all of that. Okay. And then the big question is, where are the youngest rocks in the field of view? Where do you think the youngest rocks will be in this field of view here? Will it be on the outside or on the inside?
It will be on the outside.
It will be on the outside. Why will it be on the outside?
Because of the law of superposition.
Because of the law of superposition. So, because this is a mountain, so you will imagine that it's going to be an anticline, all right? And since it has been eroded, right, the oldest beds will be at the center and the younger beds will be at the periphery of this anticline. Does that make sense?
Yes,
Yes, sir. Yes, sir.
Yeah, I just thought to introduce this exercise to you guys. All right. So I'll stop sharing.